Welcome to Section 9 of Introduction to Image Processing. This section is about tools for retouching images and reducing noise in images. Starting with noise, one common type of noise is noise associated with defective pixels. Here is an example where the defective pixels show up as pure black or as pure white, which can happen if some of the pixels are simply not working and so are either permanently on or permanently off. This kind of noise is called salt and pepper noise. One reasonably effective way of reducing salt and pepper noise is an operation called a median filter, which works by replacing each pixel with the median value of pixels in the neighborhood of that pixel. The second argument in the median filter function gives the size of the neighborhoods. Here the second argument is 1, which means 1 pixel up and down and to the right and to the left, which works out to a 3 by 3 neighborhood around each pixel. The 1 is called the radius of the neighborhood. The median filter works best when the noise shows up as outliers in a relatively uniform background. For example, zooming in on a small part of this image shows a few obvious noise pixels on a gray background. The median filter in this example goes through the image considering 3 by 3 neighborhoods and replacing the pixel in the center of each neighborhood with the median of the pixel values in that neighborhood. And since the noise is typically an outlier rather than the median, this replaces the noise pixel with the neighborhood median. If we instead zoom in on a different part of the image where the background is not uniform, then the median filter still removes the noise, but it also replaces the darkest and the lightest pixels of the original image, which reduces contrasting details. A larger neighborhood can be useful if there is a lot of noise or if the noise affects more than just isolated pixels. For example, with this noisier image, a median filter with neighborhoods of radius 1 does not remove all of the noise. The remaining noise can be removed by increasing the size of the neighborhood. Here is a manipulate input that gives a slider for adjusting the neighborhood size, starting with size 1, which leaves some of the noise. Superimposed on this image is a white square representing the sizes of the neighborhoods. Increasing to size 2 eliminates all of the noise in this example, and further increases in neighborhood size could, in principle, eliminate even more noise, but those increases give further reduction in contrast and loss of detail. Even if the pixels aren't defective, they can still be affected by noise with a normal or Gaussian distribution, which is the noise shown in this example where the noise adds a Gaussian random number to each pixel value. This sort of noise is often an unavoidable characteristic of noise in the electronics that created the image. One reasonable way of dealing with Gaussian noise is to simply average it out using a mean filter, which works like the median filter except that it replaces the pixel at the center of each neighborhood with the mean of the pixel values in that neighborhood. The mean filter is an example of a common type of image operation called image convolution. Convolution is the mathematical term for replacing each pixel with a weighted average of nearby pixels. The matrix of numbers that gives the weights for the weighted average is called the convolution kernel. For the mean filter, the convolution kernel is a matrix like this one where the weights are all the same and add up to 1. The weights are chosen so that multiplying that convolution kernel element by an array of pixel values and adding everything up will give the mean pixel value, which is what is needed for the mean filter. The mean filter is convolution with that convolution kernel, which can be done in the Wolfram language using the image convolve function. Instead of giving the same weight to all of the pixels in the neighborhood, it is common to give greater weight to pixels that are closer to the center of the neighborhood. One way of doing that is to use a matrix called a Gaussian matrix as the convolution kernel. Here is a Gaussian matrix of radius 3. It is easier to see the structure of that matrix by looking at a plot which shows the larger matrix elements near the center of the matrix. As with the convolution kernel for the mean filter, the weights in the Gaussian convolution kernel are again normalized to add up to 1 so that the image doesn't get lighter or darker as a result of the convolution. Convolution of the image with the Gaussian matrix gives Gaussian blurring, which is another tool for suppressing noise. Convolution with that Gaussian matrix is a special case of an operation called a Gaussian filter, which is done here using the Gaussian filter function, which is also in fact what is done by the blur function. These are all image convolutions with different convolution kernels. Returning to the topic of removing noise from images, all of the noise reduction operations that have been covered so far have the side effect of blurring edges and other sharp details in an image. It is often desirable to remove noise without losing those details, and there are several methods of doing that. One method uses an operation called a mean shift filter. To show how that works, here is an artificial image with lots of sharp edges and with added Gaussian noise. This shows the mean shift filter applied to that image. The meaning of the second and third arguments will be described in a moment. For comparison, here is the mean filter applied to the same image. The difference between those results can be seen more clearly by zooming in on one of those edges in the result from the mean shift filter and the same edge in the result from the mean filter. Both filters work by replacing each pixel with the mean of pixels in each neighborhood. The second argument in both functions gives the size of the neighborhood. The difference is the third argument in the mean shift filter function. The mean shift filter excludes from the weighted average any pixel values that differ by more than that amount from the value of the pixel at the center of the neighborhood. The effect is that for pixels near the edges, the mean shift filter excludes pixels that are on the other side of the edge. Far from the edges, this has no effect. The mean filter and the mean shift filter give the same result. Near the edges, excluding from the averaging the pixels on the other side of the edge decreases the number of pixels that are included when calculating the mean, which leaves more noise, but it also preserves the sharpness of the edge. Here is a manipulate for choosing the second and third arguments in the mean shift filter function, the size of the neighborhoods and the amount by which pixel values are allowed to differ before they are excluded from the averages. The goal is to choose the neighborhood size n to be big enough to give good averaging but not so big as to blur out image details, and to choose the difference parameter d to be big enough to average out noise but not so big that pixels on opposite sides of an edge get included in the same average. Whether or not a suitable compromise can be found will of course depend on the image and on the nature of the noise. Here is the same manipulate applied to the earlier image where the same issues apply in making compromise choices for the neighborhood size and the parameter that specifies the limiting difference between pixel values. Another method of removing noise but with less blurring of the edges is a method called total variation filtering. This shows the total variation filter applied to the test image. And for comparison, here is a Gaussian filter applied to the same image. The total variation filter shows roughly the same reduction in noise as the Gaussian filter, but does a better job of preserving the sharp edges. The total variation filter works by changing pixel values to minimize the variations between pixel values that tend to be associated with noise, while maximizing the variations that tend to be associated with real features of the image. The term total variation in total variation filtering refers to the sum of the variations between the values of adjacent pixels, which is the quantity that total variation filtering tries to minimize, since those are the variations that are associated with noise. The total variation filter function takes a second argument called the regularization parameter. Here is a manipulate for adjusting that parameter. The regularization parameter controls how much weight is given to reducing total variation relative to how much weight is given to preserving the original image, which preserves everything about the image, including the edges and the areas of uniform color and the noise. In many images, there are large regions like the sky or large objects where adjacent pixels tend to have similar colors, so preserving the colors of those regions while reducing the small variations from pixel to pixel tends to reduce noise. Larger values of the regularization parameter eliminate more noise, and smaller values preserve more of the original image, so as with the parameters in the mean shift filter, the idea is to find a suitable compromise. One other method that is worth mentioning here is Wiener filtering, which has applications other than noise reduction, but one feature of Wiener filtering is that, like the mean shift filter and the total variation filter, it does less filtering near edges, which of course has the effect of preserving the edges. As before, the effect near the edges can be made more obvious by zooming in on one of the edges, which shows the noise eliminated by averaging far from an edge, and both the edge and the noise are preserved for parts of the image that are near an edge. Just to summarize these edge-preserving filters, this display shows the noisy image, the image with noise reduced using the mean filter and the Gaussian filter, and noise reduced using various edge-preserving filters. The mean shift filter and the total variation filter and the Wiener filter are more complicated and use more computer time, but are better at preserving edges. Continuing on with the subject of preserving edges, it is often possible to restore lost edges in a blurry image. One simple method of adding apparent details to an image is a method called unsharp masking, which works by actually blurring the image a little bit and then adding whatever was lost by that blurring back into the original image. To show how that works, start with a clear initial image, just a grayscale image of some characters, and add some blurring such as might have resulted from noise reduction or maybe because a camera was out of focus to begin with. To sharpen the image by unsharp masking, start by adding even more blurring, and then subtract that extra blurry image from the previous blurry image, which gives the part of the image that was lost due to the extra blurring. That image is pretty dark because the difference is pretty small. The difference is more apparent if that image is multiplied by a factor bigger than 1. Here it is multiplied by 25, which emphasizes what was lost due to the additional blurring. Now simply add that difference to the previous image to get an image with edges that are noticeably sharper. Here are all three images side by side, the original image, the blurry image, and the image after unsharp masking. The sharpened image does have sharp edges, which can be useful, but those edges are of course not in the same places as the edges in the original image. Unsharp masking is what is done by the sharpen function in the Wolfram language. The sharpen function is shown here, adding some sharpness to an image. Unsharp masking is a simple process, and the results can look pretty good in applications where the appearance of sharpness is more important than restoring the original image. A more sophisticated approach to sharpening is to consider the process through which the image came to be blurry in the first place and then try to undo that process. To demonstrate how that can work, start with a clear image and make it blurry. As noted earlier, the blurring here was done by convolution with a Gaussian matrix, so in this example we know how the image came to be blurry and can use that information to undo this effect. The inverse of convolution is deconvolution, where the goal is to undo the effect of a previous convolution. Deconvolution by that same kernel gives a remarkably good restoration of the original image. Deconvolution can also be used to correct certain other image distortions. For example, this shows convolution of an image where the convolution kernel is a normalized identity matrix, which illustrates what might happen if the camera or the object was moving when the image was captured, or if the camera lens had a lot of astigmatism. The result is an image where the details of the image have been so distorted that the digits in the image are nearly unreadable. This shows deconvolution used for partial recovery of the original image, at least to the point of being able to read the digits. The details of how deconvolution works will not be explored here. This input to the image deconvolve function includes the method option, which is used here to specify the Wiener deconvolution algorithm, which is one of several possible deconvolution algorithms. The result from deconvolution is not unique, which among other things means that the choice of the method and other settings can and usually will affect the result. Also, in practical examples, the original convolution kernel is often not known and must be determined by trial and error or by some other method. Deconvolution is nevertheless a powerful and widely used technique for improving images and is worth exploring further for applications that might benefit from these sorts of transformations. One special method of image enhancement is a method called inpainting, which can be used for noise reduction but is really designed for restoring or retouching specific regions of an image. For example, here is an image with some missing pixel values, such as might be due to noise or damage to the image or various other problems. Since the defects in this example are pure white, it is pretty easy to construct an image like this one called a mask, which identifies the parts of the image that are to be repaired. Given the image and the mask, the idea of inpainting is to analyze the colors and textures and other features of the image outside of the defects and use that information to fill in the defects. There are various algorithms for inpainting that are somewhat involved and won't be described here, but several of those algorithms have been implemented in the Wolfram language in a function called inpaint. The inpaint function takes the image and the mask as arguments, and at least in this example gives a result where the defects have been filled in so well that it might be difficult to tell where the defects might have been. As already mentioned, although inpainting can be used for general noise reduction, it is especially useful for retouching specific regions of an image. For example, consider this image of a postage stamp that has been stamped with a black postal cancellation mark. Those are the black marks on this red stamp, and suppose the task is to remove the black marks. As before, this can be done by inpainting, using the image as the first argument in the inpaint function and inserting a mask that identifies the parts of the image that are to be retouched. And the inpainting again gives a remarkably good result where it is difficult to see evidence of the black cancellation marks. Probably the most difficult part of that example is construction of the mask. Constructing the mask is basically a segmentation problem where the goal is to isolate the component of the image that corresponds to the black cancellation mark on the postage stamp. There are many ways to do that. One approach involves a bit of ad hoc programming that starts by binarizing the image with an appropriate choice of threshold. That result could be used right away for inpainting, but the background is also black and so is also part of the mask, and so the entire background gets painted. One way to remove the background from the mask is to apply a minimum filter followed by a maximum filter, which has the effect of filling in the smaller white areas of the image, leaving only the background. The minimum filter works by replacing each pixel value by the minimum pixel value in each neighborhood, and the maximum filter works by replacing each pixel value by the maximum pixel value in that neighborhood, and as with other neighborhood filters, the second argument gives the size of the neighborhoods. This particular combination of maximum and minimum filters is a common operation called opening. Subtracting that result from the earlier binarized image removes most of the background. This leaves various smaller areas other than the cancellation mark. Those smaller areas can be removed using the delete small components function, which is used here to delete all of the white areas with fewer than 30 white pixels. Inpainting with that mask leaves a faint shadow of the black cancellation mark on the stamp, which happens because the masked area isn't quite big enough. That problem can be addressed by using the maximum filter to dilate those regions on the stamp and then subtracting the background and deleting the small components, which gives the mask that was used earlier. Here are all of those operations in one short program. This particular combination of operations is unique to this example, of course, but there are many examples that can be handled using various combinations of similar operations. The mask for inpainting can also be constructed interactively. For example, here is a scene with a boat in the foreground, and suppose the task is to use inpainting to remove the boat. It will be easier to draw in the mask if the image is enlarged to make it easier to draw a line around the boat. The most common interface for the Wolfram language includes an interactive tool for drawing the mask. Click on the image to bring up the toolbar, select the mask tool, and then carefully draw a line around the area for inpainting. After that, the mask can be copied and the image restored to its original size, and here is the mask. That mask can be used, as before, as the second argument in the inpaint function, and the result is an image with the boat filled in using colors and textures from the surrounding image. That's the end of the examples for this section. This section covered noise in images, image convolution and deconvolution, inpainting for retouching and restoring images, and various ways to construct a mask for inpainting. In addition to being useful by themselves, these operations often come up in preparing images for further processing.